Hello everyone, this is Nidhi from Sri Venkateshwara College of Engineering, Bangalore. My USC number is 1V23CD032 and I'm from the 4th sem student from the Department of CSE Data Science. The course code is DCS 405A and the title is Discrete Mathematics. Let us begin with the slide. So basically in this presentation, we will be seeing the Cosets and Lagrange's theorem, which is essential concept in the group theory. Within the discrete mass, we will also cover the definition, properties, and implication to provide a comprehensive understanding of these topics. Now let us begin with the coset, where coset in DMS it's a fundamental concept of group theory that helps to understand the structure and behavior of the subgroups. It is essential and important for proving theorems like Lagrange's theorem and also understanding the quotient groups. Basically, a coset is a form of subset which is derived from a group of abstract algebra. Given a group G and subgroup H, the left coset of H and G is defined as a set of all elements obtained by multiplying and fixing an element in G. Mathematically, it can be written as shown here. GH is equal to GH, where H belongs to H. Let us see some of the properties of a coset. If H is the subgroup of G, then the left coset of H is the G partition. This means every element of G belongs to exactly one left of coset H. The same holds with the right coset. Equal size, where all the cosets of subgroup H has the equal number of elements in H. It can also be denoted as mod GH is equal to mod G for where small g belongs to all capital G, which is group. Disjoint of the coset, where any two cosets are either disjoint or exactly the same. The coset representation, where any element small g belongs to caps G, can act as representation of coset GH. Also, some would be quotient set, left versus right coset, Lagrange's theorem, etc. In the discrete mass, the group theory it plays a very vital role, especially in the topics involving symmetric structure and algebraic reasoning. Basically, we focus on the symmetry and permutations, modular arithmetics, and also the graph theory. Use group actions to count the non-equivalent configuration. Coding theory, where groups are help for error detection and correction of the codes. Also, this theory helps to minimize and analyze the FSMs. Transactions can be modeled with group actions. Let us now move forward with the Lagrange's theorem. The proof of the Lagrange's theorem would be said as follows. If we consider G as a finite group and H be the subgroup of G, then the order of H divides the order G would be represented as module G is equal to modulo H into modulo G ratio H, where the number of distinct left cosets of H in G and the right cosets will be determined. So basically, this would be the representation of it. This also says that every element of G lies in exactly one left coset of H. So each coset has the same number of elements as H has, and these cosets do not overlap. The left coset would be defined as each small g belongs to capital G, which is group. It is defined, the left coset would be defined as shown like this. Coset is then partitioned into the group. Also, all the cosets should have same size. And at last, counting the elements of G, we will be proving H is equal to G. Let us state the Lagrange's theorem. which says that for any finite group G and of subgroup H, the number of elements in H, it divides the number of elements in G as well. So this fundamental theorem highlights that the relation between subgroups and the large group establishing the index of G in H, which represents the number of distinct cosets in H and G, is equal to the order of G, which divides the order of H. The implication of this theory would be that it gives a precise language to describe symmetrical properties and structure like graphs and logical gates, etc. It also allows and the classification of object based on behavior, not appearance. The application in modular arithmetic, where the groups are found for understanding the modulo operations. Also for counting and combination, where the concept like cosets and group actions are used to count distinct arrangements. This would be implicated for resolving complex counting problems by using symmetric rather than a brute force method. Concluding this video, understanding the Cosets and Lagrange's theorem not only enhances the comprehension of group theory but also provides the critical insight into the structural properties of algorithmic and algebra existence.